So as we had said, we'd be doing some prerequisites that are required to before we get into string theory, right? So somewhere you would have heard that they had said that we have in string theory there are many extra dimensions that are curled into space. Okay, so these are actually called compact dimensions. Okay, so these are called compact dimensions, and we deal with them in what we call compactification of extra dimensions. So this is the basic mathematics that is involved in that. So what is this compact extra dimension? So if we have an infinitely long line like this, okay, where we have an object like this that repeats itself after an interval, let's say 2 pi r, then and this infinitely long line is topologically the same as some circle of radius r, right? Because every time this repeats, okay, so let's say this is the point, and let's say this is of radius r. So every time you go around 2 pi r, you're going to, this object is going to come and it's going to repeat itself. So an infinitely long line is, topologically speaking, it is a circle. Okay, it is just a circle like this of radius r, where this is this object is going to repeat itself. So this we will go to mathematically. We'll talk about define it in this way. Okay, such that this is called an identification. So this is what we were talking about. So this is your x, the infinitely long line which we're talking about, and at intervals 2 pi r, it's just going to keep repeating itself, and this so this is just equivalent to a circle, right? It's just equivalent to a circle. So this is something called as an identification. So in two dimensions, okay, in two dimensions, in two dimensions, if we have such an identification for both x and y, this is topologically equivalent to a cylinder. Okay, so you can see that if after every 2 pi r, the x and the y components line just repeats itself, this can be topologically equivalent to a cylinder. So supposing now if we have an identification such that this x is so x yields minus x, then the real line yields the half line. So here you can see that if this was our point, okay, so here we have a fixed point, we call this the fixed, so the 0 is called the fixed singular point. So if x goes to minus x, then you can see that the real line is the half line. This is called R1 slash Z2. So R1 is the real line, and this identification is identified by this symbol Z of 2. Now similarly, this kind of identification we are talking about in 2 dimensions, okay, then we're going to have this kind of a rotation. Okay, so this is a rotation in 2 dimension. Here you can see z goes to e to the power 2 pi I by n. Okay, so each rotation is of 2 pi, the size of the rotation, the step, or the step, that the smallest step of the rotation is 2 pi divided by n. Okay, so here we have the identification c by z by n. So c denotes the complex plane, right? So this is the complex plane. These are rotations in complex plane, and we have zn denoting this identification. So just an example of what happens when we have these compactified dimensions incorporated into our physics. So this is nothing but a square well, right? So this is a square well potential. This is the energy of a square well potential calculated from the Schrodinger equation. So supposing we have a extra dimension y which is compactified, then what happens, right? So again, these are we'll have to separate these terms, right? So we follow the variable separation method to solve this equation, and we have a separate solution for x and y. However, the y has a identification, right? It's a compactified dimension. So this identification we have for y. So such that y plus 2 pi r will be y again, right? So function of this solution will has a you replace it by y plus 2 pi r, the argument, then you get phi of y again. So in that case we have the energy now is modified. We have a additional term L by r the whole square, where this L was the separation constant that we introduced.